Hello, talking about continuity and discontinuity. Some huge words there. Continuous and discontinuous. Discontinuous means not continuous. So let's look at some different types of discontinuity. The first type we'll call infinite, and that's right actually. My goodness, infinite discontinuity. That could be something like a graph that, say, does this business. Okay, and it might have, say, a horizontal or a vertical asymptote on there. That would be an infinite discontinuity. You could have another type called removable discontinuity, where you have a graph come up like this, maybe an open hole there, and then a solid dot this way with the graph continuing over, say, like that. That is called a jump discontinuity. Jump discontinuity. And I said removable and then drew an example of jump discontinuity. Here's removable. Say you're coming around and this thing goes like that and then makes a hole and then keeps going like this. And then all of a sudden you just got a dot right here, right underneath. That's called a removable discontinuity. So these are three different types of graphs that are not continuous. None of those would be continuous, and their limits would be quite different. In fact, the first two wouldn't have limits at this point. This one could, because as you approach each way, we'll do that in a second. All right, so that's just the different types. Now, some actual problems here. Let's say this is more theory than it is problem, but let's look at what makes a graph continuous. Okay, let's say I have, I don't know, an endpoint here, and then a thing goes up like this and has an endpoint here. All right. And let's say we're interested in some value C. We'll call it, that's usually how it's done, C. Some value C, say, right here. Right there. Well, for a graph to be, so I ask you, at this point, this interior point here, is this graph continuous? And of course it is. It is definitely continuous. There's no holes in it. There's no jumps in it. It just flows right on along there. But what makes this graph continuous is this definition as the limit of this function we'll call f of x. So we'll call this f of x and this x here. The limit of this function as x approaches c, and again, if we don't specify, that means it's coming from both directions, would equal what's called f of c. Now, what that means is if I plug in the x value into whatever function that is, it's going to spit out the y value that equals the same thing as the limit. This thing will equal the same thing as the limit. So as I, say, approach this from this direction, it's going to approach this point here. And as I approach it from this direction, it's also going to hit this point. And if I just flat out plug it in the function, whatever value this is, it's going to be the same as the limit. So the limit has to equal the function evaluated at that point. All right, now let me show you another example. Here we have one that's discontinuous. Let's say this graph came like this, came over, had a hole right there, and then a solid dot here, and it went off. Say like that. Okay, and let's say this is our value C. Whatever it is, insert random number there. Okay, I ask you, what is the limit of this function as x approaches c? Well, you would hopefully say, well, this doesn't exist. This does not exist. Because as I approach it from this direction, it's up here, and as I approach it from this direction, it's up here, and the left and right-handed rule says it has to be the same. So there's no limit to this. What would f of c be? Well, f of c is this right here. This is f of c. So this output, after you plug in the value of c into your equation, I didn't even specify what the equation was, but this would be the f of c, which is not equal to the limit because this thing doesn't even have a limit anyway. Now let's look at one that does have a limit but is still discontinuous, and I think this will make a lot more sense. Final graph here. This time, let's say we have a graph that came out like this, had a hole right there, it kept going. And then up here was our solid dot. All right. Use like that color. Does this, and we'll call this C, does this have a limit? So if this is f of x, x, and the limit of f of x as x approaches c, does that thing have a limit? Yes, it does. Okay, this is an example of a discontinuous graph that does have a limit, because as you approach this from this direction and from this direction, it would have a limit, and whatever that is would be right here. So this would be limit L, we'll call it. Okay? We'll call that whatever the limit is. Now, does this equal f of c? Because for a function to be continuous at a given point, those two things have to be equal. If I evaluate whatever function that is at c, well, it doesn't give me this hole like the limit does. It gives me this dot right here. So this would be f of c. And so f of c is not equal to L, and these two things aren't equal either. So this thing is not continuous. Remember, we're worried about the definition of continuity here. This thing does have a limit. That is the limit right there, whatever that is. This is the function evaluated at point C, but they're not continuous. This proves, this is the definition of the proof that it is not continuous. Okay? So that is a whole lot in this 6-part series on limits. And I highly recommend going back and watching all 6 again at some point before tests and quizzes and whatever. So have a good one.